Thank you very much. Today, I'm going to give the formal presentation of the new arena for the optimization problems. The title is Uniform Circuit and Logarithmic Space Approximations of Refined Combinatorial Optimization Problems. So I'm going to focus on the following things. I'm going to give some refinement of the existing optimization classes. Particularly, mostly we are interested in the polynomial time approximation schemes. And then we are actually digging down deeper into the polynomial time level. And we'll suggest using the circuit, non-uniform circuit, and the logarithmic space computation to define in optimization problems as also approximation problems. Now, so I start with the motivational discussion. Why we need this new arena for the optimization problems. As you know, an optimization problem itself is a very ubiquitous. You can find it everywhere in the world, in practice and also theory. But the most optimization problems so far we have discussed are polynomial time level. But then also there are tons of problems that are not categorized simply into the polynomial time levels. So we'll just take a look at the very general framework here. So we have the three major categories for the polynomial time optimization problems. The first one is the so-called NPO, the NP optimization problems. We have a very simple picture here. And among those problems, we consider the polynomial time approximable problems. That means we can actually approximate the optimal solutions in polynomial. And another typical likely class is called the PO. That means that we can actually exactly calculate the optimal solutions in polynomial. So if you take a look at a picture like this one here, the PO actually covers a very small area compared to the big NPO, assuming that the P is different from NP. So just to take a look at a very short tour of those problems. The first one is the minimal 0-1 linear programming problems. This is very simple. So now we have a matrix like this one here, and we have another three vectors. And we'll find a vector x that satisfies this constraint. So this is actually the set of the linear inequalities. And to minimize the inner product of these two vectors, w and x. So this problem is known to be complete for NPO, whole NP optimization problems. Another typical example is the maximum cut problem. So this is actually, suppose that we are given an undirected graph, and we are partitioning this graph into two sets. So that is called a cut. And what our task is to maximize the number of the edges that's actually crossing two partitions. For example, this is actually the cut. It may not be the optimal, but the cut is like this one. So this problem is complete for approximation, polynomial time approximation complexity class. Finally, the minimum ST cut problem. So this is the suppose that we're given the directed graph, and we have some source and sink, and we have to find cut. The one partition contains S, the other partition contains T, and we have to maximize the capacity. So that's the number of edges that's crossing one set. The other parts belong to another set. one typical example is something like this one here, right? One set contains S, the other set contains T. So this problem is complete for PO, that is the NPO problem whose optimal solution is exactly calculated in polynomial time. So now, if you just plug in all the problems into picture here, so we know that linear programming problem is the complete for NPO, and max cut is the complete for APXP, and mean SD cut is complete for PO. But if you take a look at the following problems, first one is the minimum vertex weight problem. So similar to the previous problem, we are given directed graph, and we have source node, and we have a weight function. The function assigns some natural numbers to the vertices. Now, our task is to find the path from S to some vertex. And we have to maximize the end point of this path. For example, the optimal solution is the actual path like this one, from S to V7 to V2 and V6 and V3. So the V3 node have weight 7. So this is the maximum number, right? So this problem is obviously polynomial time solvable, but it does not seem to be complete for a PO complexity class. So what is the exact complexity of this particular problem? Also, another question is, suppose we are given the set of the Boolean formulas, for example, x1 or x3, or this Boolean formula, or x1 or x2 or x3, right? We have some set of the Boolean formulas. And also, we are given an assignment. So that, for example, x1 takes true, x2 take false, for example. So now our solution is to find a subset of this F that containing the satisfying formulas. And we have to maximize the number of formulas, right? So this problem is very simple. You can actually, take a look at from the first entry to the last entry, and just picking up all the satisfying formulas, right? So obviously this problem is PO, belong to PO, but it does not seem to be complete for PO. So what is the complexity of this problem? So now, to categorize those problems into the map of the complexity classes, we really need something more inside PO. So that leads us to a refinement of the existing notions. So particularly, we are looking into the log space approximation, and also a uniform circuit, like AC0, NC1, and those very low-level circuit complexity. Now, we will give a formal definition of the refinement of the non-optimization classes. But before that, we actually use the low-level complexity classes. So the machine model is slightly different. For example, in the polynomial time setting, so we just take any variation of the Turing machines. But if you just go down to logarithmic space computation, we need something more. For example, then we have input tape, so this is the read-only, and we have work tape, so this is actually log space bounded, and we have auxiliary tape, so this is the read once. So you can't read the same symbol twice. And if you compute the function, probably we have an output tape. So this is actually write only. So we will use this particular Turing machine instead of the standard Turing machine model. And the input has this form, x, comma, y. X is given into input tape, and y is given in this auxiliary tape. So we'll quickly review the complexity classes called L or ML. So we start with non-deterministic log space. So this is actually the class of the decision problems defined by the non-deterministic Turing machines using logarithmic space bounded tape. And L stands for the deterministic version of the log space computation, complexity class. And for example, it's an SE connectivity. So this is actually the given directed graph, and sink and source and sink are given, and we have to find out whether there is a path between S and T. So this problem is known to be as an NL complete. And if you just switch from the directed graph to undirected graph, the same problem becomes L complete. So the difference between the non-determinism and the determinism is very small compared to the polynomial time setting. So you have to pay more attention to what we are doing whenever you goes down to the logarithmic space computation. So what will define the auxiliary L? So this is the taking the auxiliary deterministic Turing machine and using logarithmic space to compute to accept the pair x and y whenever an x, y belong to A. In this case, this particular set S, A, is called auxiliary L. So this is just a simple extension of the standard L. And functional version of the auxiliary L is called an auxiliary FL. F stands for the functional version of L. So now we actually go ahead into optimization problem. So NLO optimization problem. So this is similar to the NPO problem. So we just simply use instead of P, we use L, right? Well, so this is actually the very standard formalization of the optimization problem. We have the admissible instances, and we have a function that actually specify the solutions. And we have two goals, either max or min. So we are actually considering it's a maximization problem or a minimization problem. And we have an objective function or a measure function that assigns the number, particularly here is the natural number, to the solution, each solution. And what will define the min NL. So this is actually the collection of the all minimization problems that have this particular formalization. And the max NL is the maximization version of min NL. And if you combine two of them, we will just simply write NLO. If you just take P instead of L, all definition defines NPO. So only difference is that we actually switch polynomial time computation to logarithmic space computation. Now we'll take a look at the max vertex, the problem we have seen before. So this problem is nicely formulated in this way. So that actually fit into the NLO category. So this max vertex problem is an NLO problem. Next, what would define, similar to the PO, what would define the problem that is computable, or the optimization solutions are computable exactly using logarithmic space. And so that is the LO problems. And the picture shows the, it's a little bit hard to see the line here, the yellow lines. So NLO is here and NPO is here. So NLO is actually subset of this PO. And we have LO, NLO, is the subset of N and O. So the situation is pretty similar to the polynomial time level. And well, important notice is that PO, NLO is NLO. So that this means the if you just take a look at it, then only NLO problems and consider the polynomial exactly polynomial time exact calculation of the optimal solutions. This exactly calculates the NLO. So the NLO is not quite strange, actually. So approximability is defined pretty similar to the polynomial time level. And the only difference between the polynomial, though this is actually the polynomial time approximability, and we'll just change this polynomial time DTM to the log space DTM. Then we will get the notion of the log space approximability. The only difference is just the polynomial time and the log space. It's a very small change. So now for the approximability, we'll define it pretty much the same as for the polynomial time. So we have the APXP problem before. So now we'll take the logarithmic computation to define the APXL problems. The situation is like this one here. So that the APXP is a polynomial time approximable complexity class is the subset of the NPO. Similarly, the approximation log space complexity class is a subset of NPO. Similar to the previous claim, the approximation version of the NLO is exactly the same as NLO. So that the fourth NLO, approximability, polynomial time approximability, and polynomial time exact computation are pretty much exactly the same thing. And now we will take a look at it in the non-uniform circuit, AC0 and NC1. And we will use those circuits to define complexity classes. So, so this is actually the whole picture here. NPO is covering everything, and NLO is here. And we define it as an LO, and also NC1O. That means the complexity class consisting of the optimization problem, NLO optimization problem, that whose optimization optimal solutions are exactly computed by the NC1 circuit. Similarly, it's an AC0 circuit, and so on. So now, what we define as the completeness, because the optimization is actually weakened. So we have to weaken the reduction as well. Instead of the standard polynomial time reduction, we just take a logarithmic space-bounded reduction. And then we will define the complete problem. I just quickly show the definition of the reduction. So this is actually polynomial time approximation preserving reduction, so-called AP reduction. So reduction is, there is two functions. The first function actually maps the instance to another instance. And second function maps the one solution to another solution. And similarly, we can define the logarithmic space approximation preserving reduction. We will use the capital L instead of capital P to represent the log space computation. And also we can define it APNC1, APAC0 in the same way. So that all the reduction, if you just goes down, the reduction gets really, really weak. So you only use an AC0 circuit to make this reduction to be satisfied. For an exact reduction is pretty much the same as before. In a polynomial time level, so the reduction maps into one solution to another solution. But the last condition says the optimal solution have to be mapped to the optimal solution. So this is actually the exact reduction. And we will use the logarithmic space to define the same reduction. So now, finally, we'll list up a short list of the complete problems. So we have seen the two problems. First one is the max vertex problem. So this is actually an APXL complete problem. And the reduction is actually approximation preserving logarithmic space reduction. So this is actually not my result, but it was proven in 2007. And this is actually the problem using the pathway, started from source to sink, and we had to calculate, maximize the total pathway. So this is actually complete for the minimum NL using a reduction NC1. And if you take, if you restrict the graph to be a forest, then the same kind of problem becomes an APXL complete using NC1 reduction. And this is the last slide. Two more results. So we have seen the Boolean formula value problem before. So this problem is actually NC1 all complete under NC1 reduction. So the last PBO stands for the polynomially bounded. That means the major function is always bounded by polynomial. It doesn't go up to the exponential. Okay, thank you very much for listening.
You can prepare here. Any question? We may have only one, at most one short question. Okay.